Alright, so today's Electronics 210 lecture is going to be on the concepts of binary addition and subtraction, and also the concept of representing negative numbers in binary. So this was a homework problem for lecture 1. I think it was actually 2 homework problems for lecture 1, but I'm putting it in its own lecture because I kind of want to talk about representing negative numbers in binary now as opposed to when we get to binary adders later. It's going to make things a lot clear, and I just knocked something off my desk. Okay, as usual, previous lecture is linked to here, so go ahead and watch that if you missed it. If not, let's just dive right in. So adding in binary is exactly the same as adding in base 10. The only trick is knowing when to carry. So let's start with a simple addition problem. We're going to take 0, 1, 1, that's a little too far space, 0, 1, 1, 0, and then we're going to add to it 0, 0, 1, 1. So we look at the decimal for that. This is 6 plus 3. So 0 plus 1 is 1. 1 plus 1 is 2, but because we're in base 2, we can't represent a 2 as a 2, so we carry, so this drops to 0. We carry a 1. 1 plus 1 is again 2, so we drop the 0, carry a 1. 1 plus 0 is 1. If we add that up and convert to decimal, we get 9. 6 plus 3 is 9. Everything works. So it's a fairly straightforward process. The only trick is knowing when to carry. If you add two things and the result is greater than 1, you should do a carry. Okay, so let's look at another example, because this example is actually a little more useful. We're going to take 1, 0, 0, 0 and add to that 1, 0, 0, 1. And this is binary 8 plus binary 9, which should give us binary 17. Now, if you're paying attention, because you should be, you'll note that 17 is a bigger decimal number than we can represent in 4 bits of binary, because we're doing 4 bits math here. So what we're going to see here is what happens when this occurs. So 0 plus 1 is 1, 0, 0 is 0, 0 plus 0 is 0, 1 plus 1 is 2 with a carry, so we carry, and we end up with a 1 over here. Now, this one is special. It is outside the 4 bits we have allowed for, and is called a carry out. Carry out is the name given to the bit that occurs after a single bit or multiple bit operation, arithmetic operation. Carry out's the extra bit if you have something left over. So you can perform a single bit operation, get a carry out, or you can perform a 4-bit operation and get a carry out. It's whatever is left over at the end. Now this is a very special carry out because this is also called an overflow. What's an overflow? An overflow is where this bit is actually meaningful to the number. It means that if we counted this along with all the other bits here, and we took this as a 5-bit number, it would be a useful 5-bit number to us, meaning we'd see 8 plus 9 as 17, and not 8 plus 9 as 1 with a carry out. There is a difference between a carry out and an overflow. We will see a carry out situation where there isn't an overflow, and we'll talk about that later. So that's addition. I'll write that somewhere. This is binary addition. It's fairly straightforward. Nothing going on here. Nothing that hard. It's fairly straightforward. So let's talk about binary subtraction before we get into talking about negative numbers. Binary subtraction, exactly the same as binary addition. The trick is to know what to do when you have to carry, or as it's called in subtraction, borrow. So let's take, we'll use a 3-bit system this time. So we'll take 1, 0, 0 minus 0, 1, 0, which is binary 4 minus binary 2. And we'll do a subtraction. 0 minus 0 is 0. 0 minus 1 you can't do. So what do we have to do? We borrow. So this becomes a 0. This becomes a 2. 1 minus 2 is, or 2 minus 1 is 1, and 0 minus 0 is 0, and there you have it. So 4 minus 2 is 2. The trick is to know what to do when you have to borrow and when to borrow. So if you have 0 minus 1, you have to borrow. So let's look at another situation. We'll do 1, 0, 0 minus 0, 0, 1, which is binary 4 minus binary 1. So 0 minus 1 you can't do. You have to borrow. You can't borrow from this because it's 0, so you have to borrow from here. So this becomes a 0. This becomes a 2. You borrow from the 2. This becomes a 1. This becomes a 2. So 2 minus 1 is 1. 1 minus 0 is 1, and 0 minus 0 is 0, and what you're left with is a binary 3. Again, everything checks out. It's very straightforward. It's not that hard. Now, the trick comes when we do something like this. We're going to take 0, 0, 1 minus 0, 0, or 0, 1, 0. Now, this is binary 1 minus binary 2. And thus we get to the concept of negative, I don't know why I put that in parentheses. We get to the concept of negative numbers in binary. So, what happens? 1 minus 0, straightforward, that's just 1. 0 minus 1. Well, okay, we've encountered this before we borrow. But we're at the most significant bit, and we can't borrow. So, what do? This should result in a negative 1. So what we have to do is figure out a way to represent negative numbers in binary. Now, this is a sticking point for me because a lot of people that teach this will teach negative numbers in binary, I think, 3 different ways. Most of them are useless. I'm going to teach the one that's actually useful, and that is the concept of the 2's complement. That is a terrible writing. Complement. There we go. Note how this is spelled. This is complement, not complement. That's an E there. Complement. Because this should also be about proper spelling as well. Okay, so the 2's complement. Or negative numbers in, but I'll just copy that and I'll put it down here. There we go. Recycling. Oh, whoop, that is old. Let's try that again. Copy and paste. There we go. So negative numbers in binary. Okay. So the way 2's complement works is I'm going to explain it simply, and then I'm going to explain how you get from a number to 2's complement. So let's take a 4-bit system, a nibble. Get that terminology down. And let's say we want to represent the number negative 4. How do we do that? Well, 4 bits. 1, 2, 3, 4. You start by assuming that the first bit is a signed bit. That means that this does not represent, this is 4 bits, so this would represent 8. This now represents negative 8. And then you add on to it these bits, which are positive, in order to get to negative 4. So these are positive, this is negative. So you start with negative 8, and then you add on numbers to get to negative 4. So negative 8 plus 4 gives you negative 4. And that is how 2's complement works. First bit, the most significant bit, is the signed bit, and that becomes the negative MSB value. And then you just add on to it values, positive values, to get to the number you want to represent. Now this can be said more mathematically. This is the actual process. So we'll use the number negative 4 again. And we'll take the number, well, we'll take negative 4, which is, we'll take the absolute value of negative 4, which is 4, which is the number you start with. You want to negativize 4. So you start with the number 4, which is 0, 1, 0, 0. If you want to use 2's complement, you have to use one more bit than the minimum you need to represent this number. So 4 can be represented in 3 bits. To make it negative 4, you're going to have to represent it in 4 bits. So you start with a number. So start with a number. And this is used to negativize any number, as you will see in just a moment. You invert the bits, so this becomes 1, 0, 1, 1. And then you add 1. So this becomes 1, 1, 0, 0. And thus you're left with, this equals negative 4. So start with the number 4. Get rid of this. Start with a number 4, which is 0, 1, 0, 0. Remember, one more bit than the minimum number of bits to represent this number. Invert all the bits, and then add 1, and that's how you get the negativization of it. The reverse process also works, so you can start with negative 4, which represented as the 2's complement, as we saw, was 1, 1, 0, 0. So start with a number. You invert the bits, 0, 0, 1, 1. So invert, and then add 1. And then you're left with 0, 1, 0, 0, which is 4. All right, clean that up a bit. So this is used to negativize. It's the only word I can think to make this make sense. Multiplying it by negative 1. That's how this works. Okay, so I bring this up because we can think about subtraction. So if we talk about the process of subtraction, if you take a minus b, it's the same thing as saying a plus negative b. So subtraction is just addition of the 2's complement. So let's go back to this example we had here. So I'm going to copy this and paste it down here. Paste, there we go. So this is 1 minus 2, and then we're going to take the 2's complement of 2. So I should shift this down so it's on the line. There we go, that's clean. So 1 plus the 2's complement of 2, which is 1, 1, 0. So this was negative 4 plus 2 is negative 2. So now this is 1 plus negative 2. And then you just add. 1 plus 0 is 1. 0 plus 1 is 1. And 0 plus 1 is 1. There you have it. You now have negative 1 in 2's complement. So that's how this works. Now, let's talk about an interesting case. This is the case I mentioned at the beginning, or near the beginning, where you can have a carryout but not an overflow. Actually, before I do that, let's talk about the what is the number wheel? Some people call this. So we've got we use a 3-bit system here, 0, 0, 0, and I'll just fill these in. Okay, so fill those in, and then we're going to look at the magnitude and then the 2's complement. So 2's complement. So magnitude, this is 0, 1, 2, 3, 4, 5, 6, 7. 2's complement, 0, 1, 2, 3, negative 4, 5, not negative 5, negative 3, negative 2, negative 1. So right here, right as it gets to the most significant bit, it gets flipped, and then you start counting up. So up, up. So from negative 4 to negative 1, and then from 0 to 3. So something you can probably note from this is that the max value of a 2's complement, so the magnitude goes from 0 to 2 to the n, minus 1. I feel like there's a better way to represent that. There is 0 dot 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 2 to the n minus 1. 2's complement, on the other hand, goes from 2 to the n minus 1 to 2 to the n minus 1 minus 1. So this will go from negative 4 to 3. That should be a negative sign there. Negative 4 to 3. So you have the same range. There we go. You have the same range, you just shift it down a certain set of numbers to get negative numbers. Now, this brings up another point, which is sort of more useful for the computer side, programming-wise, which we'll get to way later, but it's worth mentioning now, is this concept of what you look for is what you get. So if you look at this binary number and you want to look for just a magnitude of it, you're going to find 7. If you're looking at this as a 2's complement binary sequence, you're going to see this as negative 1. So it's all about what you look for. So I'm going to give you problems with this, and you should obviously know which is which. So I'm going to have to tell you that, okay, this is a magnitude, this is a 2's complement, work with that. I'm not just going to leave you not knowing what's what. When you do programming, however, it's not that easy, because you can store something as a signed number, using 2's complement, and then retrieve it as an unsigned number and get a completely different value. So it's worthwhile noting that what you look for is what you get. What you store it as is not always what you're going to find it as. Little tangent, but I guess it has homework implications. Okay, so back up to that case. Carry out without overflow. So you can have a carry out without an overflow. So what I'm going to do is I'm going to add 0, 0, 1, and I'm going to add 1 and negative 1. See, this is getting back to what I was saying. Yeah, see? You can look at this as a magnitude and say, oh yeah, this is 7, but 2's complement, this is negative 1. So I'm going to tell you this is negative 1. What happens when I add these two? It's the same thing as saying 1 minus 1. 1 plus negative 1. So we'll add these. 1 plus 1 is 2, so drop, carry. 1 plus 1 is 2, carry, carry, and then carry one more. And then what we have here is the carry out. Come on, erase. Carry out. Now, this isn't an overflow. What should 1 minus 1 be? It should be 0. And if you look at all these bits, it's 0. The only error here is this overflow, this carry out. But the thing is, it's not an overflow. So an overflow, what happened there? Overflow, there we go, occurs when carry in does not equal carry out. Now carry in, see how I'm carrying from one bit to the next? I could just as easily bring in, ooh, wow, that was very weird. I could just bring in another one here. That's called the carry in. This is the carry in, that's the carry out. Now you're looking at this and going, wait, there's no carry in. I'm not bringing in any extra numbers, so this still has to be an overflow. There's a carry out, but there's no carry in. If we go back to the definition of the 2's complement, the last process is, or the last step in the process is adding 1. So what we can say is 0, 0, 1, scroll down a little bit more, 0, 0, 1 plus 1, 1, 0 with a carry in of 1. Now if we do this, so this is C in. If we do the process, we get 0, 0, 0, 1 with a carry out. But because carry in and carry out both equal 1, this is no overflow. If this was an overflow, it wouldn't make any sense. We've now added a bit that shouldn't be there. When we set a 2's complement, we essentially set a cap to the max number you can have. Adding an extra bit throws a bit of a wrench into our counting system. So what we have to say is, no, this carryout isn't an overflow. We didn't make an error. There's no extra bit. The numbers aren't bigger than we had allowed for. It's just a mathematical hiccup. It's a little extra. So you can ignore the carry out and just look at these. So what we're left with is just a 0. And so that is when a carry out is not an overflow. Now if we scroll back up here to where we first got our carry out and overflow, there was no carry in. Now, yes, you could make the argument that this is a 0 with a carry in of 1. However, if you make that argument, you are implicitly saying that this number here is a 2's complement. So there are two ways you can look at a number as being a 2's complement. The second way is the first way is I tell you it's a 2's complement. See, I've told you that this number here is a -1. It's obviously a 2's complement of 1. Second way is you can look at, here it is, you could look at an expression like this and see there is a carry in, so this number must be a 2's complement. It's sort of an implied thing. If in my homework, if I do that, I'm saying this is a 2's complement. If not, it's obviously a magnitude. So that's how I'm going to do the homework. Speaking of the homework, there is going to be homework on this. It's just going to be straight binary addition, subtraction, and calculating the 2's complement. Nothing too hard. Pretty much everything we did here. We're probably not going to go above a nibble, so everything is going to be 4 bytes or less. So pretty straightforward. So I guess that is it for this lecture.